Dear students, this is Dr. Venkatachalapathi, Institute of Aeronautical Engineering. I am going to discuss on some of the problems related to metal casting, in that especially the solidification time. In the solidification time, some of the problems where they can ask in the competitive examinations like GATE, IES, and some central government job exams. Okay, so here majority of the student they thought that manufacturing process is a simple theoretical subject, so we should ask only simple pattern making, mold making, types of patterns, and what are the important type of casting methods, etc. But especially for the designing of gating system and designing of the how the solidification time. So in general, as you know that in a metal casting process, first you have to prepare the pattern and pattern making, and you can able to do the some hand molding or machine molding technique where you can able to prepare the mold cavity. Parallelly, they can able to do it for the some other cupola and some furnaces making the molten metal. We have to take under the molten metal from the furnace to the mold cavity place, and by pouring the molten metal into the mold cavity, and we should wait for certain cooling time called the solidification time or quenching time. So during this quenching and this solidification time only, there is a structural changes in that metal, and also because of that only that strength and some of the properties also can be improved better. Okay, so look at I'm going to discuss some of the problem in that. So look at especially the problems in solidification time mainly focuses on this solidification time of a casting. Look at any manufacturing process, especially the metal casting process. The only thing is how you can pour the molten metal into the mold cavity. Look at the first one, there is a 5 seconds that solidification time. So the filling time 5 seconds, 1 minute, 2 minute, and 6 minute. So what is the variation of the solidification time of the casting to be provided in order to have some good properties? Okay, good properties, especially this calculation of the pouring time and some of the solidification time. These can be calculated with some scientists like Kohlmann's rule, and some scientists in the Rosenthal. These people has been identified how much time to taken to fill the molten metal into the mold cavity. How do you determine that pouring time? And after pouring, how much time to give the cooling time? That is called solidification time. If you give the proper solidification time, then only the component has a flawless component or defect-free component can able to produce. Yes or no? So look at in this case, what I am going to give a brief idea about this thing. A different type of solidification of the casting in a some alloys and metals and etc. How it can able to work easily. So in this solidification time of the problem, so let us see the some concept involved in this. So in general, in x-axis there will be a time, y-axis temperature. So here there is a high pouring temperature, and whenever once it has been reached the high temperature, then we should provide some cooling. So either maybe liquid cooling, and how the liquid cooling will be taken place, and how the freezing can be done starting to the end point, and how do you determine the solidification time for local and the solidification time for the total, and which is what how we can able to complete the freezing starting to freezing end. Okay, and what about the freezing temperature and solid cooling? So here another interesting thing I would like to discuss here. So in any general that cooling curves for the phase diagrams or iron carbon diagram like that, you can see the, so there will be a solidus line and liquidus line. So this is called the above this liquidus line. Liquidus line. This is solidus line. Solidus line in between liquid plus solid. In between liquid plus solid. That is called the where you can able to draw the cooling curves from certain stages. And whenever the initially at the high temperature, the pouring temperature is high, suddenly we should provide some cooling. So whenever the above the liquidus line always is a liquid solution, below the solidus line will be always solid, and in between only liquid and solid combination. So in the first cooling curve, this x1, so there is some part of liquid, and that liquid we have to add that solid also, but percentage wise 20/80 and 30/70 and 40/60 like that. So whenever this total principle involves in the that crystallization, that is how the growths of the grains, what about the changes of its structure and all, it will happen. So whenever heating the metal to above its recrystallization temperature, in the recrystallization temperature speaks out the term recrystallization can be defined as the transformation of old nuclei into a new nuclei, old nuclei into a new nuclei. So initially that granules and the structure will be small, and it will enlarge. Okay, so whenever it is a solid cooling and some solidification time, what will happen? That molecules will be enlarged, and again it will become one small molecules. Okay, so all these processes will comes under the some quenching process, or we can also call it as solidification time of the casting. So that is what you can see. There are the 4 stages about the solidification time. So initially you can check the 6 minutes if you give the solidification time, what about the component inside. If the 2 minutes is given, what about this inside? And if the 1 minute is given, how about this component? And 5 seconds is given, you can see the comparison, the all the component while giving the what you called that solidification time or quenching. So normal cooling. So obviously depending upon the cooling can be increased, it can see the clear cut structure of the that metals and the metal of the castings. Okay. So this is what about the how the solidification time can be calculated in any type of process, and that we'll discuss in detail in the another case study problem. Okay. So I hope the student now let us see the some important problem of the solidification time. These type of problem they frequently asked in the gate examinations. Okay, so look at in the problem a cylindrical shaped part. So that is called cylinder. Cylinder means there is a radius. Top and bottom is a circular in shape, and height will be the h. A cylindrical shaped part is to be cast out of aluminum. Here the material is aluminum. Material is aluminum. Okay, and the radius of the cylinder, that small r is 250 mm. Radius of the cylinder is 250 mm, and its thickness is h. Height is thickness is 20 mm. Okay, if the mold constant, that cm, mold constant cm, or also called b, this is almost all 2 is given, 2.0 second per mm square. So this is Corona's rule. So actually in the last session I explained about the Corona's rule, how long will it take place the casting to solidify. So this is what Corona's rules means. Solidification time. Solidification time can be explained B into volume divided by surface area whole square. This is the general equation as per the Corona's scientist has been derived this formula. Solidification time is equal to some constant factor B. That B is nothing but a what you called mold constant Cm, mold constant, which is given 2.0 second per mm square, and V is the volume of the object, that is a cylinder means we can determine volume. And what about the surface area of that cylinder? Okay, these two things is very important. Look at the surface area is equal to uh, top one circle, bottom one circle, pi r square plus pi r square, that is called the 2 pi r square plus 2 pi r h. Okay, so the surface area is bottom one circle, top one circle, 2 pi r square, then plus 2 pi r, pi d into h, this height pi d into h, that is the surface area. And coming to the volume of the cylinder is pi r square h. Volume of the cylinder can be explained with this formula. Volume is equal to pi into r square into h, where r is nothing but the radius of the cylinder and h is the thickness of that cylinder. So this is the problem, how we can able to solve this. Clearly look at. So the solution is, first we should determine the area of the cylinder. So for example, we can take this as a cylinder. So in the cylinder, the radius is given. Okay, this is small r, which is equal to 250 mm, and height h is nothing but 20 mm thickness. H is 20 mm thickness. This is smaller. Okay, and as you discussed about the area, surface area, you can see the 2 pi r square plus 2 pi r h. You can substitute the values in this formula, and so the 2 pi r square plus 2 pi r h, 2 into pi into r is 250 whole square plus 250 2 pi into 250 r into h is 20. So if you simplify this thing, area will get to 4 4,24,115 mm square. So this the surface area of the cylinder can be obtained. And similarly, if we take the volume, what is the volume? So the volume can be volume of the cylinder can be expressed in the simple formula, which is called pi r square h. Pi r square h, in the sense pi into r is given that radius of the cylinder is 250 whole square into h is the 20 mm. Still you can simplify this equation with the calculator. This is also called 39. Okay, 39 lakhs 26,991 mm cube. This is the volume of the cylinder. Okay, surface area, volume. And as you know that according to the Cornell's rule, that solidification time xt, which is equal to some constant into v by sa whole square. This is a standard formula to determine the solidification time. So here the b is the constant, we which is given 2.0 second per mm square. So that you can substitute here 2 into, and volume is, you got it 39 lakhs 26,991 divided by some surface area is 4 lakh 24,115 whole square. Okay, so this volume by surface area whole square into the constant factor that cm is equal to 2. When you simplify this, you will get to 171.5 seconds. If you convert this into minutes by 60, okay, by 60, you will get 3.86 minutes is the solidification time for this application. Okay, so this is what how we can able to determine the a simple formula, and how do you solve this problem. A cylindrical shaped part to be cast out of a metal is aluminum. The radius is, which is given by 250 mm, and thickness is 20 mm. If the mold constant cm is equal to 2.0 second per mm square, in this Cornell's formula is b into volume by surface area whole square. Okay, so with this formula you can easily determine how much time it will take to casting to solidify it. Okay, so look at, in this case, area which has given 2 pi r square plus 2 pi r h, and volume is pi r square h. Sphere volume is pi r square into h. Okay, and this is the solution. Area is 2 pi r square plus 2 pi r h. You will get the 44,24,115 mm square. Similarly, the volume of this cylinder is pi r square h. So you can substitute the value of r and h in this equation. You will get the 39 39 lakhs 26,991 mm cube. And according to the Cornell's rule, the formula is simple. X is equal to V into V by surface area whole square. So because of this 2 into what you got, this volume by surface area whole square. You can simplify it, you will get 171.5 seconds. You can convert the seconds into minutes by 60, you will get 2.86 minutes. Even if you convert this minute into hour, divide by another 60, so that you will convert into some other purpose. Okay, so this is what about the important problem in the Solidification Time, some case study which has taken from these references. The Science and Engineering of Materials, 6th edition, Boston uh, scientist, and this is the Cengage of Learning. And another textbook called Groover, The Fundamentals of Modern Manufacturing, 5th edition, John Willis and Sons. With these references, I have collected the problems and how do you solve this problem easily. Okay, so I hope all the students understand clearly about this case study. Okay, in the next session, one more case study problem can be explained in this solidification time. Okay, so thank you, students.
Like, share and subscribe. Hit the bell icon for more updates.